Hey y'all, this is an online lecture for our class. We're going to be doing some work today just looking at probability distributions, which is really kind of underpinning a lot of what we'll be doing the rest of the semester. A lot of statistics historically have been focusing on how do you go from small samples to larger samples, how do we make inferences from small samples to try to forecast what's going to happen in the future. And so this is kind of looking at different ways that we've modeled what are the probabilities of specific outcomes. So that's another way of saying, so I'm going to run through this lecture. There's going to be a couple of exercises. There'll be a check at one point to make sure you've done this work. Um, so that's another way of saying that much of statistics is really a probability game, right? So when we're talking about stats, we're not talking about certainty. And I think this is one of the really complicated things about statistical analysis and communicating statistical analysis is that we're not saying what's going to happen, right? What we're saying is what's likely to happen. So we can see this, for instance, in this is Hurricane Irma a couple weeks ago. The cone of uncertainty that we don't know exactly where the hurricane's going to go, but we know where it's likely to go. And one of the issues here is how do we forecast that uncertainty while also giving people a definite enough message that they take things seriously. And that's kind of a continuing issue with any kind of statistical analysis. But that's really what we're doing with statistics is we're modeling probability. We're saying what's likely given either mathematical odds of an outcome or past history and what we know about the way the phenomena have behaved in the past, right? So when we think about these outcomes, we can separate them into a couple of different categories, right? So we can think about discrete outcomes. These are ones that have a finite number of possibilities. So you could think about a dice roll, right, as an example of that, or ones that have continuous outcomes where there's an infinite number of possible outcomes. These would be things like rainfall, right? You can have 5.372 inches of rain. You can have 5.374 inches of rain. Basically the same, but slightly different from one another. So we could run through some of these and just think, run down these and think about, is this discrete or continuous? So a number of cars parked in a single lot, say probably more discrete. It would depend on the size of the lot though, right? What if it's got 500 spaces? Treat it more as a continuous outcome potentially. Times between transit bus arrivals would be continuous outcome. Number of 90-degree days each July though would be a discrete outcome. There's 31 days. How many of them were 90 degrees, right? There's a fairly fixed number, somewhere between probably 20 and 31, right? For given that month. So you can get a sense of how these are put together. Why that matters is because when we're thinking about probability of an outcome, with discrete outcomes, we think about what is the probability of a specific outcome, right? So number of 90-degree days in July, what's the probability that we'll have 8 of those? What's the probability that we'll have 9 of those? With continuous outcomes, we can't really ask about specific outcomes. What's the chance we're going to have exactly 5.7325 inches of rain? We can do that, but it's going to be really small. Instead, we ask questions like, what's the chance we're going to have between 5.5 and 6 inches of rain? We ask about ranges, right? And when we get into talking about normal curves, that's the way that we talk about normal distributions. We don't talk about it in terms of a specific value necessarily. We talk about a range of values. You know, what's the chance that you'll get 90% or higher on an exam would be an example of that. So we're going to talk about 3 different kinds of distributions today. I'm going to move my little window here up. 3 different types of distributions today: the binomial distribution, the Poisson distribution, and then briefly the normal distribution. We're going to spend more time on that when we meet together on Friday. So we'll spend most of the time on binomial and Poisson distributions, which are 2 types of discrete outcomes, as you can see here on the map. And really the Poisson distribution is a form of the binomial distribution. So with the binomial distribution here, we're asking what's the probability of 1 out of 2 outcomes? What's the probability that something's going to happen, right? Is it going to rain or is it not going to rain? Are you going to get a 7? Are you going to get another weather? Is there a tornado? Is there not a tornado? Was it over 90 degrees? Was it under 90 degrees? You've got a yes or no kind of answer. And the question is, how many times will you get that outcome? How many times will you have a day over 90 degrees over X series of trials, right? So will it be over 90 degrees on 5 out of 20 days, right? So that's the outcome that you're getting here. So when you look at this graph down here, along the x-axis, this is how many times that outcome happened. And up here, this is the probability. So is there a 10% chance of getting 2 outcomes in whatever number of trials that you've got, say 2 out of 12 in this case. There's a 25% chance of getting 3 out of 12. That 3 times out of 12, you'll get whatever outcome it is that you're measuring. So x times over n trials. That's how a binomial distribution works. And the shape of a binomial distribution varies depending on the number of trials that you've got, right? So if the probability of an outcome is 0.5, meaning it's 50%, it's basically a coin flip, and you flip that coin 20 times, here's what the distribution looks like. The most likely outcome is 10, right? Which makes sense. The odds are 50%. If you do a binomial distribution, and notice this is pretty spiky in terms of the distribution. I believe that is a platykurdic distribution is the name of that. The you got same 50% here, but 100 trials, right? Here is the distribution for that. Much more mesokurdic. It's much more like what you'd expect a normal curve to look like, much more spread out. The center of it, mean, is still 50, but it's not nearly as compact as when we only had 20 trials. And then the blue here shows 100 trials, but a probability of only 0.3. And as you'd expect, 30% of the time, 30 out of 100 trials, right, is the mean of that distribution. Notice the shape of this is fairly similar to the green, but it's a little more spiky, I think, because it's a lower probability. So the range of possible probabilities is lower in that case, right? Put this back over here. I'm just going to leave this here. So to calculate a binomial distribution, we follow this rather daunting looking formula. And so let's just kind of take this apart for a second just so you understand how it works. So this formula right here tells us the probability of a certain outcome. And to do this, we need to know a few things. We need to know what's the number of successes that we're testing for. That's x. So x times out of how many trials, right? And that's arbitrary. That's something we pick. So what's what we're saying here is the probability of x over on the left-hand side. We need to know the number of trials we're going to do. How many times is this outcome, could it happen? And then we need to know 2 other things, the probability of success and the probability of failure. Now these 2 are connected, right? So this p plus q equals 1. And you could, if you know p, you can calculate q because it's just 1 minus p. And there's, I'm sure, good statistical reasons why it's put together like this. I can't explain them to you. This is not n. This is n factorial, if you remember your high school math. So it's n times n minus 1 times n minus 3. So if it was 5, right, it would be 5 times 4 times 3 times 2 times 1 is the way that that works. And so we do this. We do the number of trials factorial, the probability of success to the x power, the probability of failure to the n minus x power. So we're testing, what's the probability of having this number of successes, and n minus x would be the number of failures, basically. So what's the probability of failure? X factorial, so the number of successes, and then n minus x factorial. And you'll notice that you've got these 2 connected here. So you don't need to know why that is. You can take a stats class if you're interested in finding that out. But that's just the general idea of the formula. So let's just see how this works. If we had a deck of cards, which we would if we were meeting in person, the probability of getting 2 pair in one hand, this is, if you're a poker player, right, you would know how all these hands probabilities work, because it's really how poker playing works. The probability of getting 2 pairs in a 5-card hand, so 2 7s and 2 9s in the example that you see down at the bottom here, is 0.48. You basically have a 5% chance of getting, in a random deal, 2 pairs. Right? So we know that the probability of success mathematically, this is something we can determine just through looking at the possible hands you could get out of a 5-card deck, is 5%, which means that the probability of failure is 95%. You're probably not going to get 2 pairs in your hand. 95% of the time, that's the way it's going to work. We want to know the probability of getting 1 2-pair hand in 3 separate deals. So over the course of 3 hands, will we get at least 1 of them? So our x, our number of successes that we're looking for, is 1. And our n, our number of trials, is 3. 1 success and 3 trials, right? So we can do the math here. So we've got 3 as our n factorial. We've got the probability of success is basically 0.5 to the x power, or 1. And then the probability of failure to the n minus x, 2 power. then we've got x and n minus x factorial. We do all that math and we figure out the probability of getting one success in 3 hands is 13%. Still not great, right? But at least it's better, right, than 5% in terms of what we're looking at. And notice that it's not just you just add it up 3 times. It's a little more complex than that in terms of the way that it's set up. This isn't 15%. It's 13% in this case, just because of the way the statistics work. All right, we could do the same thing. So what if we wanted to say 2 or more 2-pair hands? So what if we want to do cumulative possibility? We'd have to calculate each one of these separately, right? So 2 or 3 or 4 or 5 2-pair hands. We'd have to calculate the chance of each one of those, which we could do. We could go through and calculate each one independently by hand. That would be fun, but we're not going to do that. And then add all those up, right? So you can say the probability of this plus the probability of 3 plus the probability of 4 plus the probability of 5. The cumulative probability there is 2%. So really not a high chance that you're going to get 2 or more 2-pair hands in 5 separate deals in this case. So what I'm going to, well, if you wanted to, you could go through and do this. For instance, you could say if the probability of 3 of a kind is also 5%, you could say what's the chance of getting 1 hand with 3 of a kind in 5 separate deals. Why don't you pause the video for a second and try to work that out. I'm going to stand here for a second while you pause the video and try to apply this formula. Okay, so hopefully you've unpaused the video now. Let's take a look at what this should look like, right? So the response would be your n, right, is 5 separate deals. Your probability of success is 0.475, and you put that to the x power. Your x is 1 number of successes, right? The probability of failure is 1 minus 0.475, basically 95% again. And you have 5 trials minus 1 success, so 5 minus 1, n is 5, x is 1, right? You get that number, and then n minus x factorial, so 5 minus 1, that's 5 times 4 times 3 times 2 is 24. When you work all that out, you get a probability of getting just 1 hand of 3 of a kind in 5 deals is about 20%, 19.6% in this case. So hopefully that makes sense to you all. Okay, if we were in class, we would try this and actually deal 5 poker hands and see how many 3 of a kinds we get. We don't, we're not, but if you wanted to do it in spare time, you could. You should get it about 1 out of every 5 trials, right? So 20% of the time when you deal 5 hands, you should get a 3 of a kind as one of those 5 hands. Okay, so that's binomial distribution and how binomial distribution works. The other distribution we're going to talk about today is the Poisson distribution. It's named after this guy, Simeon Poisson. I actually need to move this down slightly so you can see his name. There he is. And it's a little bit different. So with binomial, both of these deal with binomial outcomes. So Poisson distribution is also saying what's the chance of getting a certain number of events. But instead of saying over a certain number of trials, right, where you've got like we're going to roll the dice 10 times, how many times will we get success? Here we're saying over a certain period of time. So within a given period, how often will an event occur if that event occurs randomly? We know generally how often these things occur, right? So you can think about like big floods, right? We know that, you know, once in 100 years we'll get a flood like this, or 2 times in 100 years we'll get a flood at a certain level. Given that we know that in any given year, what is the probability that we will get a flood like that? So with Poisson distribution, you need to know the probability of success, so it's expressed as a probability. Here in a Poisson distribution, we have something called a lambda, which is the expected frequency. How often would you expect to see this event based on past observations? So binomial distribution, you have a mathematical probability. Here we've got observed frequency of event. So this table compares the two of them. They're similar, right? Because the Poisson distribution is basically from the binomial distribution. It's saying we have something that occurs really infrequently. The probability is really low. So the chance of getting a hurricane in Georgia is relatively low on any given day. But we can still say over the course of 10 years, we expect to see maybe 1 hurricane, right, hit the state. 2 hurricanes hit the state, especially, I mean, it's probably a little more frequent than that. You get the idea with it. So with a binomial distribution, like I said, you get a statistical constant. It's often mathematically derived. Poisson distribution is observed frequency. Binomial distribution, you have number of trials. Here you've got per unit of time or space, how many events will happen per state or something like that. Here you've got number of outcomes versus rate of occurrence. That's not that different, but you get the idea in terms of the way that this is set up. So as lambda increases, as the frequency increases, if you kept the number of time, units of time the same, right? If you said how many in a given year, how many tornadoes occur in Georgia, right? If you say lambda is really small, generally we get 2 tornadoes per year, right? Or 1 tornadoes per year, you'd get a distribution that looks like this. Very low probabilities of getting a tornado. But if you say 10 tornadoes per year, right, you get a distribution that looks much more normal in terms of the Poisson distribution. And in fact, the normal distribution is just a one of these binomial or normal distributions with an infinite, or binomial or Poisson distributions with an infinite number of outcomes in the way that it's set up. So the formula for a Poisson distribution is somewhat similar looking to the binomial distribution. It looks simpler, and you only need to know really one thing, which is lambda, right? So you've got E, this is the statistical constant E, so 2.718, right? Or you could take it up to 2.71828. E to the negative lambda power, and then lambda to the x power, and x here is the same thing. How many occurrences are you testing for, right? How many expected occurrences would you have over x factorial? So it's pretty straightforward in terms of the way that we calculate Poisson distribution. So let's just look at an example here. Given that Georgia has an average of 21 tornadoes per year, what's the probability of a given year having exactly 15 tornadoes? Right? So here our lambda would be 21, and our x would be 15. We're saying 21 average occurrences of tornadoes, and I don't know if that's actually true. I made that number up, just so you know. What's the probability of a given year having exactly 15? That's our x. We're just saying, here's how this works. And so we'd work it out this way. The probability of getting 15 tornadoes, e to the negative lambda power, lambda to the x power over x factorial, it works out to be 4%, right? A fairly low probability. It would be higher if we went higher up there. One of the nice things about a Poisson distribution is that you can use it to test whether an event is actually random, right? So a given Poisson structure assumes randomness. If you look at the probabilities of certain outcomes, you could say, for instance, the number of 90-degree days in the last 50 years, here's what we observed, here's what we would expect to see, given what we know about the frequency of them. And we can see in this example, for instance, that it's much higher at the high end, that we're seeing more 90-degree days at the high end, given what we would expect to see in this case. So that there's something going on that might be moving temperatures up, right, in that case. So just, we're not going to work too much with that, but just be aware that Poisson distributions can be used to test randomness, right? Okay, so here's another chance for you to pause and try to work this out. Let me just get rid of my camera here. So this is, those of you who've seen the movie, regrettably, or read the book, more happily, Cloudy with a Chance of Meatballs. There's a town of Chew and Swallow that gets food storms, right? That's the shtick with the book. The town of Chew and Swallow receives random spaghetti storms 1 day out of every week, so 1 day out of 7 on average. A neighborhood wants to have an Italian picnic, and what's the chance that it will receive 2 storms in the week prior to this event so they won't have to cook? So what you need to do is identify what's lambda, what's x, and then you need to work out the probability of x. So go ahead and pause the video. I'll stand here for a second while you hit pause. Okay, so hopefully you've done the math on this. Let's take a look and see what it would look like. So lambda in this case is 1, right? The average number of storms per week that we're seeing. And we're looking to see, well, what's the chance they'll get 2 so they'll get enough food so they don't have to cook? So if we work out that formula, right, e to the negative lambda, so you've got e to the negative 1, lambda to the x, 1 to the second power, over 2 factorial, we get 18%. There's 18.4% chance of getting 2 storms or more. They probably should plan on cooking, but there's a decent chance, 1 out of 5, they might get 2 storms ahead of time, or maybe they can just freeze up over the course of a couple weeks, use their chest freezer. So that's binomial and Poisson distributions. We're going to talk next time more about normal distributions, which are somewhat different, but they are super helpful and very common in statistical analysis. It's unlike binomial and Poisson distributions, it's continuous, so we calculate, we have to use calculus technically to do this. Luckily, people have done that for us. But you calculate area under a curve, so it's a calculus kind of operation because of that, and you're calculating what's the probability of a range of outcomes, right? So in statistics, we're actually really interested in what's the probability of getting something that's basically from 2 standard deviations below the mean to 2 standard deviations above the mean. We'll talk about that next week with central limit theorem. What we're interested in is the probability in this range somewhere. So it's really helpful in that sense. It's not that common in real world data. We often have to transform data to make it normal, but that's the way it looks. So hopefully you all are having a good break from class today, and we'll see you in class back on Wednesday. We're not going to actually do, I think, an online check for this, but I do want you to make sure you've covered this material, as it's going to come up in the lab and in the stuff we're doing in class. So hope you have a good Wednesday. We'll see you on Friday.